Hi, my name is Steven. My objective of putting this video out here is to help those who need more explanation of statistics lectures in SUSS. As such, it does make reference to their syllabus and follows it loosely. I also want to say that it's completely normal to spend a lot of time on this mod, especially for those who don't come from a math-heavy background. And I hope this video can help fill in any logical gaps you may have about the lecture slides. As my focus is to share my intuition on how to approach a topic, there may be a couple of notational errors, and I appreciate if you let me know if I missed anything. So I feel other videos do a good job in covering joint, conditional, and discrete probabilities, so I'll focus on these four topics: continuous probability, sampling distributions, confidence intervals, and hypotesting, and how they relate to each other. So I'll start with high-level overview of probability and statistics. And in general, there are two things that we can have, which is like model of a situation, and then we can also have observations of the situation. So given a model, we want to calculate the probability that a certain observation occurs. This direction here is probability, right? And give some in the other direction, given some observations, we want to derive our model that is statistics. So I hope this clarifies the distinction, the difference between probability and statistics, and as well as how they are related. So given a model like a distribution or like a normal distribution where you know the mu and the sigma, what is the likelihood that x is less than something is an observation, and we want to calculate the likelihood of that, which is like a concrete number like 0.5, 0.8. And going the other way around for statistics, we're given a bunch of observations like samples, and then we're asked to estimate mu and sigma, and that would be statistics over here. Okay, so let's create our running example of employee working hours in a week, and let's call that x. All right, and let's say we are given the model over here, and we are asked to calculate the probability that an employee works between 40 and 50 hours a week. Okay, so we are already given the model, which follows a normal distribution of mu and sigma squared. All right, so now let's substitute in the values in our running example: 45 hours and variance of 16. Okay, so I'm already assuming, right, we know how to put this down into their language, which is the question of 40 and 50 hours a week, question mark, right? So we expect a number over here between 0 and 1, like maybe like 0.5 or 0.6. So if so I'm assuming you know how to calculate this expression over here in Excel. This in Excel. If you don't, I think you should go and look it up on how to proceed like this. Yeah, like this kind of thing. You must know how to calculate it. Get comfortable with it before coming back and proceeding with this video. So visually, like we would like to represent it like this, right? Mu of 45 over here. Okay, and then we're gonna find 50 is over here, and then like 40 is over here, and then we want to find the area under the curve, which represents the probability. Okay, visually it's represented like this, and of course we can just punch it into Excel, but how does Excel know? So people in the old days, they standardized this into this thing called a standard normal distribution, which you can think of it as a map of a real city. Let's say this is a real city, and then this is the map of it, scaled down like 100 times and centered at 0. So this is the standard normal distribution, where instead of x over here, instead of having this kind of equation over here, we have this other equation where z follows a normal distribution of 0 and 1. So this is x over here, and this over here is z. So they're not they don't represent the same thing, because this talks about the area, or like the x values in this domain, not the real city, but the map of the real city. And then we also need to apply, how do we get from the real city to the map? And how do we get from the map to the real city? It's through scaling factors. Scaling factors, like maybe 100 times, but in this case, you can think of it as a scaling formula, where it's z equals to x minus mu over sigma to get from your real city into the map. So we'll just need to apply this scaling factor to get from the top to the bottom. You can also apply something somewhat of a reverse to get from the bottom to the top, but I'll tell you when to use each and why it works. So continuing from what we wrote out in your language over here, right? What we need to do is to get, because we know mu and we know sigma over here, what we need to do is convert this x into some kind of z. So p, let's just copy the equation currently. And because we know x is related to z through this equation, let's subtract mu from all three, this, and this. So let's say this, which we do know, right? And then let's divide by sigma for all three, which makes sure that they are the equivalent, right? So this is equivalent to this. Okay, agree? So this expression itself is equal to z, and that's what we're told, right? The mapping function. So we're given this over here to be converted into z, because they are equal, right, over here. And then we have 40 minus 45, which is our mu and sigma. Okay, so we'll get some kind of value. So apparently it's minus 1.25, 1.25. So we'll get this on the map. So on the map, the z values are the same. That's 1.25 and 1.25. So we'll go find the area under the curve, which is the probability. Should be along the lines of 0.7888. Okay. So that's how you convert from top to bottom, calculate the probability, and this shaded area is the same. 0.7888, 0.7888 over here. Okay, so now we want to ask the inverse question, which is this one over here. Okay, what hours do the middle 90% of employees work? So this question could also be what is the top 10% or the bottom 20%, and you have to choose a different kind of inequality. But we're going to write for the middle 90% of employees. We're choosing this because firstly, it is middle 90%, so it's symmetrical, and it will help us draw similarities to later topics. The important property I want to highlight about this map z over here and the real city, which is whatever your distribution is that both areas under the curve like over here and over here, both sum to 1. This is a critical point because it will mean that we have an equivalent starting point in each space. So what this means is that we can always start from a desired probability on a map, like let's say the 90% of employees, right? We can actually find 90% on this real city, and we also find the 90% on the map. That's what I'm trying to say. Whether they're Z2 and Z1 or your X1 and X2 differs, that's a scaling problem. But we're able to say that 90%, 0.9 out of 1 fall between this bar and this bar on this real city, and this bar and this bar on the map. And that's a very important point, a very important property of both the real city and the map. And that's why we can start with this. We're in the map space right now. And we can convert this eventually where we want to get to is some value x1 in x, x2, 0.9. So how do we end up converting this? Let's also convert it using our scaling formula. And this time, we notice that the z is essentially x minus mu over sigma. So we can directly substitute that in, right? Because they are the same. So z equals, basically it is the same as x minus mu over sigma. We don't touch the rest because this is merely a substitution, not anything from the... We're replacing the entire expression z. We're not minusing anything from z itself because z doesn't appear in this here. So we don't need to do anything to the left or right hand sides, just for clarity. So because we want x to be in the middle over here, just x. What we need to do is multiply this to all three, right? So we do this, c1, right? Multiply to here, and this cancels off. These are same expressions, and then we want to add sigma, mu after that. And then we plus mu here, which cancels out this, so it becomes x, and then we plus mu over here. And essentially, these two expressions are now the same, are equivalent. And because we have our map, we can find z1 and z2, and we are already given mu and sigma. We can actually convert this into what is x1 and x2, which is the middle 90% of employees' working hours, lower bound and upper bound. So now we want to find z1 and z2 from our map. Okay, so just for clarity's sake, I'll just redraw this over here. And that is 0 because it's our map, and this is z1, this is z2. In between, the area is 0.9. So this is 0.05 in the tail, 0.05 of the area in the tail. Okay, so how you find z1 is you want to punch in your norm dot inverse 0.05. Okay, then give you z1. Yeah, I think if you come on the next side, negative 1.645 or something like that. Okay, or you can just consult the z table, which people did in the old days. So you can see that your lower bound x1 is minus 1.645 times sigma, which is 4, plus 45, which is the mu, equals to something like 38.42. And this is 1.645 times 4 plus 45, 51.58. Okay, I don't know if these numbers are accurate, but the point still stands that you are able to find your lower bound and your upper bound for your middle 90% of employees. Okay, so all that we've covered so far sits fully in probability land. Okay, where we know the distribution, right? The mu and the sigma. And now we'll be moving slowly, but not entirely, into the statistics world, where we will have the observations and which is let's say x, right? Then we also have the average of observations, which is x bar, and we want to find the model, right? Find mu, yeah, sigma. We usually want to find the population mean there, so that means a lot more to us than the x bar. So we want to approximate it. So in real life, we usually don't have sigma either, but for textbook purposes, they sometimes give the population standard deviation. So I mean, I think in the slides it's mentioned that if x follows normal, then your x bar will also follow a normal, but the values inside this one and this one, sometimes they do differ, right? So let's get an intuition of that. But first, also, if it follows normal, then x bar follows normal, but also if n is greater than some large number, then your x bar will also follow this formula by central limit theorem. Okay, so let's focus on this guy. Okay, so if this mu, this is sigma, right? This would be mu, and this would be sigma over square root and this little funny contraction. Okay, kind of looks funny, right? So let's go back to our running example, right? If you of people working in a company, the working hours per week. If we randomly select employees in a company, like they're not from the same clique, for example, the same department, and we ask them truthfully about their working hours, some will tell you above average and some will tell you below average. And this average, when I say average, I mean the sample average. So by definition, right, in your sample, you can't have all your points be above your sample average, because that will contradict the definition of sample average. Okay, but regardless, the idea is that the deviations when you ask in a sample will cancel each other the more people you ask, right? So the more people you ask, your sample average becomes more stable until you expand your sample to the entire population, right? Then that becomes mu, which is what you want to find. So a technique I want to share is to substitute in values into a formula to get a feel of it. So let's say you ask one person, okay? So say your x bar. Say your n is 1. How would this look like? How would the distribution be drawn? Right? It will be something like this, right? Because this square root 1 is equivalent to 1. Okay? Let's say we ask 100 people now. Now this is not 1, this is 100. Okay, so it's divided by 10, right? Now it will look like this, right? Because this whole expression, when this thing increases, this whole expression drops. And this is talking about how fat the tails are. How much probability is there inside this tail compared to this tail? So you can see that your curve becomes higher and thinner the more people you ask. And finally, let's say, right, you expand this value, your n, to infinity, right? What would this become? It will become something like this, right? Your x bar will be n, and this will be as n is close to infinity, so square root infinity is still infinity, right? And anything divided by infinity is close to 0, right? So this will be 0 squared. It will be basically this mu itself, this line. So I want to reiterate, in sampling distribution, we know our mu, and we know our sigma, and we know our n. And we want to ask questions about x bar. We want to ask questions like, is x bar greater equals 31 point something, right, in a peanut packing factory, when we are given mu 48.5 and sigma is 0.25, right? And that x bar follows the normal distribution. Right, we're given n, 25, right? Given sigma, sorry. And then we're also given this one. Then we're asked questions about this probability x, right? So this is probability, not statistics. But eventually, you see, right, that as n increases, our x bar will converge on this known u, is known, this unknown. The probability will be 100% that it converges here if n equals pop size. Okay, so how does this relate to statistics? Okay, so the confusion here is that they share the same formula over here, right? But instead of given this and this, given this and this guy, and asked to ask questions about this guy, we have given the instance of this guy, one instance. Okay, one instance, and then we're asked this guy. We may be given sigma, but we'll be asked about mu. So visually, what does it look like? Visually, it looks like this. We are given an x bar here, an instance. So now we are centering it around x bar, not mu. And we're going to think that the distribution is going to look something like this. Oh shit. Sorry, this is the old distribution. And we're going to think that the distribution looks something like this. Centered around x bar. And we're going to ask, what is the interval plus minus x bar? Do you think this mu, which is now is unknown in this case, and this is known, so here, does this mu sit within plus minus, how much is this? And given the central distribution, central probability of, let's say, 0.9. So in that case, we can go back to our map. Not the real city, but a map, right? Where in the z space, it is 0.9. Z space, z1, z2, probability is 0.9, a standard normal distribution, right? Where z is x bar minus mu over So as you can see, this expression is being used again. But now, instead of isolating for x bar, which we did over here, try isolate for x, okay? We'll try isolate x, right? Or if you were to do it again, x bar. But now, what if we isolated for mu? Because you see, mu appears on both sides, right? We transfer the mu outside of this. But what if we transfer the x bar outside instead of mu? What expression will we get? Okay, x bar minus mu for square root n. Okay, so z1, and these are known. This is known also, right? And x bar is also known, right? Only this guy is unknown. So we want to put that in the middle, in the center. Okay, so then after that we want to, so eventually you can reformat this entire expression into mu x bar minus z star, which is the absolute value. This one might be like negative 1 point something, so you just take this part rather and not the x. Okay, and x bar plus z star equals 0.9. Okay, so the probability that mu will lie between x bar plus this and x bar minus this is 0.9, which we can map it back to here, the confidence interval around x bar plus z, and then over here this lower bound will be minus z star n. And whether mu lies in between, the probability is 0.9. As you can see, if we increase the probability of this to 0.99, then this would be way larger, right? We'll be shading a larger region under the curve. And this allows a greater confidence of where the population mean will lie based on our sample mean. So next I'll go through the intuition of this formula. Okay, so mu will be within the x bar plus minus z star. Okay, so currently we have a few things that influences the formula. Have n, sample size, number of sample size, and we have this one, the sigma, which is how varied is my sample. Do I have a lot of outliers? So it's like it's higher if more outliers. This is lower if less outliers. Okay, and then we have V star, which is the absolute value because plus minus is taken care of here, which is higher if we need like confidence is 99%, okay, for concrete example, and lower if confidence is like, let's say 90%. Makes sense, right? Because if z is on the 0, 1, if 99%, if this is 90%, if this is 90%, then your z value would be closer to 0. And if this is 99%, the new z value is further from 0, right? So it's higher, and for 90% it's lower. So let's walk through the intuition of this. As we increase the sample size, as sample size increases, this confidence window can shrink. So as we get closer and closer to the population size, if this becomes infinite, this denominator becomes infinity, this expression becomes close to 0, this expression close to 0, and then mu will just be x bar lower bound and x bar upper bound. So that confirms the validity of the position of n in the confidence interval formula. If the population is more varied, assuming we're given population here, but if you use a t distribution, it will be a sample variation. So if your sample is more varied, then you will be less certain about the population mean. So if you sample, let's say, the running example, right, of working hours per week, if someone has works 5 hours a week, then someone works 99 hours a week, then you'll be less sure about where the population mean lies. You'll be less certain. That means that we will have to expand our confidence interval in order to deliver the same confidence level, like 99%, right? So you have to increase it if there's more outliers and decrease if there is less outliers. If you sample people, or if they tell you that the population variance is low, let's say maybe 44 hours and someone tells you work 46 hours, then you'd be, I am more certain that the population mean possibly is 45, right? You're more confident about that than, let's say, if someone works 5 hours and 99 hours a week. Sigma or S, the letter S, in the case of a t distribution, makes sense that this thing over here will be in the numerator. So lastly, we'll move on to this, or the t star, in the case that they don't give sigma, in the case they give S, sample standard deviation. So if a question asks for high confidence, like imagine they ask for, let's say, 100%, right? I want to be super sure, no errors, that population mean is inside your confidence window. Then you just take the entire thing, right? We'll need to expand our confidence window to infinity, plus minus infinity, because mu will definitely lie inside negative infinity and positive infinity. So can you imagine now, let's drop it by a notch. From 100%, let's say they ask for 99% confidence interval. So you can imagine that the window is smaller. And indeed, see, if the confidence window is smaller, right, you should shrink it, because this is also in the numerator term. So if this goes down, your whole confidence window over here will also shrink. You want to have higher confidence, you have larger window. And if you have you're okay with a lower confidence, you can sample less and have also a smaller window. So to recap, we first use the property of the real city and map. Real city and map having the same area under the curve, we use this property over here once again, which gives us this formula over here, which is the same as earlier. Over here, right? To choose the middle 0.9, middle 90%, right? Because confidence interval is around a certain x bar. So, but however, we only just choose, instead of choosing to isolate x previously, we choose to isolate mu. So we choose to isolate mu instead of x bar, because we know x bar now. Previously we were given mu, right? So that's why we put mu outside. But now we know x bar, so we put x bar outside and put mu in the center, because that's what we want to find. Okay, so thing based on this, CI construction is done. So let's finally move on to hypo testing. So in my opinion, confidence interval is closely related to hypo testing because we are also given or we are able to calculate the X bar in a one sample hypothesis test, and we are also asked to comment about the population mean mu, right? Yeah. So let's write down our first case of hypothesis testing, which is the two-tailed test. So let's say at the 95% confidence level, or you want to say 5% level of significance, the same thing. We want to have our H naught, and using our running example of employee working hours, we want to have H naught. We're going to say that the default is that everyone works 45 hours a week, H1 not 45. Okay, so this looks a bit different from CI, but we'll show how it pretty much is the same. So given some, let's just set up our example fully, write it down X by 7. Like I said, for CI as well as hypothesis testing, we are either given this or we can calculate this from whatever's given. So and also, let's say sample standard deviation is, let's say 4. So in that case, because we're only given sample and not a sigma, we will be using the T distribution rather than the Z. Up here we use the Z, but we can interchange it depending on whether sigma is given. So let's say Renault, then say n is 25, and then that will mean that our degree of freedom is n minus 1 is 24. Okay, so we know from on top here that our CI can be constructed using like this, x bar plus minus t s over n. So we want to put in our degree of freedom and our left tail, which is to draw it out, clarity 0 in our map. Then this side is a T distribution. This 0.95, this will be 0.025, this will be 0.025, and this will be T star, and this will be positive T star. Okay, right, 0.025, 24. Okay, so we can use this formula to construct the confidence interval, and which would be 47 plus minus 2.064, something like that, times 4 over 25, square root of 25. So this would mean that the mu lower bound will fall between 45.35 and 48.65. Okay, so 45, which is over here, of H naught, is not inside the CI. Means this CI is constructed with 95%, right? So at 95%, it's unlikely that this mu of 45 falls inside our safe range, right? It's unlikely. So it means we reject H0. Okay, but before we go to the other method, right? Let's note that why this step isn't commonly used is this thing is in the real city. If you were to use the map analogy, this is on a map, right? This would be values in the real city, which is basically hours worked per week of the employee. So you see, we actually came back to the real city values, right? But in fact, we can just utilize this value and convert this into the map value. Okay, so this here is negative 2.064 and this is positive 2.064. What the test statistic suggests us to do instead is convert this into the map equivalent and test it directly against this, rather than bring the map value into the real world. So how would we do this? This is 45, right? So let's take our test statistic. T is x bar minus mu over s over square root n, and then we know this, so we can find t. So it's like 47 minus 45, I think, and then over 4 over 25. So this will give some value which apparently is 2.5. So because our test statistic is outside 0.64 over here, right? Now this is t. From this t over here is this t is outside this 0.64, and this is 2.5, I think, apparently. Then we reject h0 because their reasoning goes that this t is greater than t star, and t star is 0.64. Which is essentially the same thing if you look at it in our map diagram. Only because these values were converted back to a real world, real city, right? And then used with mu, which is also the real value that we're trying to calculate, whether it's inside or outside, right? And the conclusion is outside, right? And if we decide to convert this mu into the map value, right, using this test statistic to get this value on the map, right, our road map, right? On the road map, it's also outside this test value, which says the same thing, outside the 0.95 region. So this test statistic method is almost similar to our CI construction method. So we've just covered the two-tail one sample test, and I'll now show how each or both methods generalize to the one-tail one sample test. So let's follow our running example again, the working hours per week. So our sample mean is 47, same as above. Standard deviation is 4, sample size 25, and yeah. Okay, so right now, so above was the hypothesis was these two over here. So now let's say the hypothesis was now hypothesis is that is more than 45, and HR wants to find if people work less than 45 hours a week. Right, so if we draw out the distribution, T distribution centered at 0, we will want to take the top 0.95 for alpha level of significance 0.05. Right, so this here is 0.05 area under the curve. This will be our t value. Okay, so let's start with perhaps the CI construction method. But instead of using just the above formula like this, we want to be a bit more careful in how we substitute it. So we have to go back to how we actually derive this formula, and we need to start with something like this over here, but the t version of it, because we're not given sigma, we're given s. If we were given sigma, it will be exactly the same. So I want to say that t star, okay, lies between t star and positive infinity, right? This thing goes all the way to infinity, and this will be area under the curve 0.95. So if we do a substitution of the test statistic, which is this guy over here, we can't substitute this guy because this guy is the actual value on the line, right? It's this guy here. Okay, so we substitute this guy instead. And less than positive infinity and t star. So apparently this guy, his value is negative 1.711. Okay, right. This makes sense. That this point on line, t and positive infinity is 0.95. This is exactly what's on the diagram here. So what we're going to do to find the confidence interval is multiply all these three by this guy. So minus 1.711 times s over square root n. Okay, then we'll bring a minus x bar, apply a minus x bar to everybody, leaving minus u. Okay, and positive infinity times this guy and minus this guy over here is still positive infinity. So eventually what we want to do is we want to get rid of this negative sign. So multiply negative 1 to everybody, and in essence flipping these signs. So why do we have to flip it? Let's say minus 3 is less than minus 2, less than minus 1, right? So if we want to have 2 in the middle, right, multiply negative 1 to everybody, right? So it will be 3 and 1. 3 and 1 first. And then what is the sign? I kind of gave away the answer just now, but obviously the signs flip. So by subbing in values, you can actually tell what you want to do with it. So this one becomes a negative infinity, which goes on the left, and less than this one, your population mean, and less than, and this thing, everything becomes positive because we multiply by negative 1. So it's x bar plus 1.711. And of course, we know this value, we know this value, we know this value. Right. So the CI construction will become something like negative infinity x bar plus 1.711, which this expression, if got it right, substituting it is 47.37, right? So notice that it's a flip case, that when we do CI, it's not always in the middle, right? It doesn't always follow the sign. Actually, it's actually kind of flipped. Notice that if we're asking this question, we're going to get a lower bound of negative infinity and an upper bound value. So we can imagine that if we're asking the opposite of this question, that is H0 U45 and H1 mu greater than 45, you can imagine that it would be something like sum x bar minus 1.711 square n and upper bound of positive infinity. Even though we're asking like less than, and over here we're asking more than for h naught. Okay, so this is something to keep in mind too. That's a bit tricky to remember. Okay, so then we can go to a test statistic method or the critical value method. You just want to sub in this, which is t is 47 minus some 45, which is this guy over here, over 425 square root 25, and then that will give us like some 2.5. So since this is negative 1.7 and this is 2.5, which is somewhere on the right over here, t from here, this is inside the safe region of 0.95. Okay, and this is a rejection region. Okay, I don't know whether to call it this word or not. Okay, so it's not in the rejection region, and therefore the conclusion over here from test that a critical value method is fail to reject h naught. Okay, and for here, this is negative infinity to 48. So 45 does lies inside the 95% CI that we have constructed for one tail at, yeah. So conclusion would be within interval fail to reject h naught. So both of them come to the same conclusion, and this method, so both methods can be used for the one tail as well as two tail one sample hypo test. So a lot of this is kind of similar for the other versions of the hypo test, which is like the two sample, for example, the PET t-test that is mentioned during the lecture slides. What you have to do to convert it to this format, this kind of single mu kind of question will be to take a mu difference, right? Is it equal 0, greater equals 0, less than equals 0, and then after your h1 is your the other side of things, like not equal 0, for example. So that can do two sample hypo test, and for the PET one, because this d is just the difference, right? PET, and it can also do the pool because you just choose a different test statistic. So maybe u1 minus u2 greater than 0, for example. We just need to choose a different test statistics, the one that's provided in the slide. So this one still uses the t or z test stat, which is also our mapping function, and our mapping function and stuff over here that we used, right? Here and here, right? It uses something t or z for the difference because you only got one. For this one, I think you use some x1 minus x bar 2, then you multiply it by some expression, yeah, something like something like that. This might not be exactly accurate, but you get the idea that as long as we have our framework, we can plug in the different test stats to solve different kinds of problems. So actually all of them are interconnected and grounded in CI test statistics and our map of the real city. So yeah, I think what only remains is like just some practice, and I hope this video does help those who are struggling with stats.